run me through it. What did you guys do for our first problem? Okay, so in order to add our fractions, we need to make it so that they have a common denominator. So how did you guys match the denominator here? Richard, what'd you do? Okay, so we need to, over here on the left, we've got an x minus 1. We need to introduce an x plus 2. And if I'm doing that to the denominator, I need to do the same thing to the numerator. Perfect. And then over on the other side, what did we need in our denominator? An x minus 1 on top and bottom. And so we get 2 times x plus 2 plus 3 times x minus 1 over x minus 1 times x plus 2, which is giving us 2x plus 4 plus 3x minus 3 over x minus 1 times x plus 2. I got 5x plus 1 over x minus 1 times x plus 2. Okay. What's slightly different, not much different, but ever so slightly different about this second example that we have here? Okay, so the denominators are more similar, certainly. They're definitely more similar. And you're correct that they are not the same. What do I need to do to get them to match then? Yeah, the only thing I need to do here to get these denominators to match is just multiply the leftmost fraction. If I multiply the leftmost fraction by an x plus 2 on top and bottom, then I should be good. I should have the x plus 2 squared that we need. And so this would be 3 times x plus 2 minus 1 over x plus 2 squared. And I'll leave as an exercise to the reader to simplify that ever so slightly. Okay, so stuff that we're very familiar with, adding fractions, we got really, really good with that, particularly not just in this class, but then in this class when we were doing our trig stuff. That is not the kind of problem that you will be given. The problems that we will be given are doing the reverse. It will be starting with something like this and working it back to something like this. Let's try and see, though, if we can't make some observations that would maybe be helpful. We could fully derive a formula for this. I don't want to. It's a little bit obnoxious and involved. But I just want to get a kind of a feel for where these terms come from. Where did we get this 5? It was the 2x plus the 3x, which came from this 2 and this 3. Which actually, if we took that back further, would be that 2 and that 3. Although that's not actually always the case, but often it will be the case. Okay. And then where did this plus 1 come from? There's the 4 minus the 3, which came from the 2 times the 2 and the 3 times the negative 1, which combined together to make this 1. So here's what we're going to essentially be doing here, all right? We are going to be constructing a systems of equations in which we take what we are starting with, in this case, the 5x plus 1, are going to equate it to some unknown values in our numerators. In this case, some generally we use like a and b, some unknown a and b, in order to figure out what is essentially going to be the decomposition for this particular fraction. Let's look at an example. Okay, so looking at our very first example here, I have 7x plus 1 over x squared plus x minus 6. In order to do this decomposition, what do I kind of need to know first? Yeah, the factored form of the denominator. I think that's a really, really good place to start. So we are going to establish first the factored form of the denominator. What are two numbers that multiply to make -6 that add to make 1? 3 and -2. So this is 7x plus 1 over x plus 3 times x minus 2. And the claim here is that if we can do the decomposition that we saw in the previous example, we should be able to break this apart into a over x plus 3, some value of a over x plus 3, plus some value of b over x minus 2. So that's our claim. That's kind of our goal here, is to find the values of a and b such that this is true. So what would you guys do from here? How could we make our right-hand side match more closely to what we have over on the left? We actually we're gonna leave the 7x plus 1 alone for now. There's actually isn't even really anything that we could like factor out there. We have a couple of options here. Yeah, so Mary's suggesting here that we could just do the same thing that we did for the first two problems. If we match the denominators, then we can actually do out this addition and make it more similar to what we have on the left. Alternatively, we could multiply by the denominator that we have on the left. Someone in first period suggested that. You'll get the same thing. There's nothing wrong with doing that approach. The way I've always done it, though, is I try to just think about it as like matching the two sides. And so to that end, what would you guys multiply by? Yep. Very nice. All right. I get in this case a times x minus 2 plus b times x plus 3 over x plus 3 times x minus 2, which we can multiply out. This is ax minus 2a plus bx plus 3b all over this denominator of x plus 3 times x minus 2. From here, I'm going to kind of treat this, I mean, it's not similar to some of the problems that we were doing in like Unit 10, but at least conceptually right here. Do we have any things that are like terms? Kind of like terms. We could group the A's and the B's. We actually kind of already have it grouped as A's and B's. I would like to group this as the X terms and the constant terms, right? In this case, I'm going to write this as A plus B times X plus negative 2a plus 3b over our denominator. And now, for the system of equations, what should this be equal to? And what should this be equal to? Blue should just match the coefficient in front of the x term from my original, should just be equal to 7. And the purple, magenta, pink, whatever, should be equal to 1. And so we get here a system of equations. This is going to be that a plus b should equal 7, and negative 2a plus 3b equals 1. How would you guys solve this system? We could do substitution, certainly could. Could solve, do like subtract b from both sides and then plug in. We could also do elimination if we multiplied the top line by like 2 and then added the 2 lines. That would also work. Since we suggested substitution first, I'll do substitution first. So this is a equals 7 minus b, which we can then plug in here. So I get negative 2 times 7 minus b plus 3b is equal to 1. Distributing, and I'm going to combine like terms and move everything over. I get that 5b should be equal to 15, which gives me that b is 3 and a is 4. And so the partial fraction decomposition for this particular rational function is a, which we said is 4 over x plus 3 plus 3 over x minus 2. Questions with our first example here? Good question. No, it doesn't matter. If we had started out with a over x minus 2 and b over x plus 3, we would have gotten that a was 3 and b was 4, which gives us the same decomposition. Yeah. So no, we don't have to be particularly caring about order here. Other questions? Next Monday. Yeah, 1 week from today. All right. This is our kind of most basic case here, where we have nice, clean linear factors and are able to do the decomposition pretty readily. So that one's not too bad. But we saw from like this second example here that sometimes when we have linear factors that it doesn't work out so cleanly. So I want to start with, let's take a look at our kind of next example here. And I want to try and approach this one like we did the previous one, and then we'll see why that approach won't work. So let's look at this. This is 6x minus 11 over x minus 1 squared. If we were to try to do with this example, like what we did with the previous example, what would we expect this decomposition to look like? I think that that is an incredibly logical thing to assume, that we would expect this to look like a over x minus 1 plus b over x minus 1, right? Those are the two factors of our denominator there. What's the issue? What's different about this example? Yeah, Sanjeev. Yeah, the denominators already match. Right? We already have it such that we can go ahead and add these together. At that point, there's no like reason to like that, like we're not going to be able to make these match. When you have a linear term that has a power, or actually any term that has a power in your denominator, the way we do the decomposition changes ever so slightly in such a way that it will match this kind of decomposition that we see here. So if I have a term that has a power that is squared, the way we are going to deal with that is we are going to look at one term where it is just the linear, in this case, x minus 1, and then one term where it is x minus 1 squared. That's true of powers of 2, and that's probably the main thing that we will look at. But I will kind of make an aside here. If we had like some function, if this was like 6x minus 11 over x minus 1 cubed, we would need essentially 3 terms to our decomposition. We would have one that is linear. We'd have like an a over x minus 1. We'd have one that was squared. And then we would have one that is cubed. No, you wouldn't be able to. You can't assume that this is 0, essentially. Yeah. Basically, you would get, yeah, it'll create some algebraic problems like later on down the line. Okay. So try this example. Find A and B. Well, that's what you're gonna have to do anyway. So I'll see or like this. Broke it out like that. Try. So the you want to take the line out so like next to you minus x. Which is what I'm about to make everyone do. But...
What the heck is that?
That's so dense.
What's this?
So, like, this one, it'd be better to leave it out. Or you want us to kind of.
So what do I have to do to this term, to make the denominator? Remember, we're always trying to make the this.
Oh,
Yeah, we actually don't even need to multiply by this. Well, what is this sum going to look like?
Oh.
I just keep going back to get
X minus your favorite.
And then you're going to get your system. In this case, we're going to get term. Yeah, this looks great. So what is our constant term? What is our, those are going to be our cost programs. Perfect. And then what's our coefficient term going to be? A. And what should those equal? So you're going to set up a system of equations here to find A.
What about is 11?
Yeah, would equal -11.
Oh,
Yep. And then what would the 6 equal? A would just equal 6. A equals 6.
Yeah, but you know,
I like this. I like that. What was the system that you got? Do we have?
I thought it was.
So wait,
But this is part of the constant. This guy. Think about it.
Eight X equals 6.
plus B.
Then we saw her.
But A is easier because A is 6A,
Because there's already a
so
negative.
it has to be 6.
So.
I don't know, it's
Yo.
I focus better on how to listen, but not.
So what do we have to do to
That's like the basis of this.
Multiply this by.
So there's a faster one.
Hiccups, theory,
Yeah, does this.
process of purposes. That's now.
Actually,
Just change.
So is there like.
Oh, no, it's like, and also because we don't get Black Friday.
Yeah, I don't think I did.
So like, there's nothing
Compared
like
to last
mathematically
one.
wrong about what you did. You just have an extra on the bottom. Cool. So then what is your?
They returned it to us. Like they returned our money. They did 8 times. They changed the years of their life. With my
And then
dad's.
what would the denominator?
Instead of that, what should, what is your?
So now we're losing money, because now the work that the price is like, you know, 6, 7, like, I would rather now, how to get money for that, because I get iPad, and they shouldn't be doing this.
Right, I have to go.
So like, bro, what
If he gave you.
yeah,
You don't
it's
get that money, so.
you're losing money, because now it's becoming funny. It's not like-
So, yeah, so that's fine. Because.
But we're using, you know, because it was $400 profit missed on the side. Exactly, that's what I was like, what do you want about, we got it, what do you?
This.
Actually, we bought another one, but the lower floor,
We're not-
all on this big things, not the one size, so we had to return it.
One A plus B.
And we returned it, it said, we'll buy it.
This looks good.
From like returning.
It's so hard.
And then my brother's like, it's all.
When you draw the heart. I know, but we're.
He gets it, his deal's on.
Another roll.
Yours.
You told me you were gonna tell me what to do. I said, do you know what the deal with finding my brother?
I probably just need the. I think you're trying to step this.
Yeah.
One line is. Coefficient.
I typed.
So.
Eats right.
What's like a word?
Every day, that's the deal. When I come on, I got no, I don't. Okay, no.
All right, let's take a look at what we got here. How did you guys start this problem. What'd you guys do? Awesome. So in this case, in order to make the denominators match, I don't need to do anything with the rightmost term. I just need to multiply by x minus 1 here on my leftmost term on top and bottom. That gives me ax minus a plus b over x minus 1 squared. Plus b, sorry. For x minus 1 squared. What here is our coefficient term? And what here is our constant term? Let's say if I make this my purple, we'll say this my green. What am I highlighting from my equation, Brady? Yep. Very nice. We've got our coefficient, which in this case is just the a. And then we have our constant terms, the negative a plus b. And so I get the system, which is that a should be equal to 6, and negative a plus b should be equal to negative 11, which when a is equal to 6 tells me that b should be negative 5. And so I get that this is 6 over x minus 1 minus 5 over x minus 1 squared.
Just leave x out of it.
You can include the x. You divide both sides by x first. Yeah, I saw some people who, and this is totally fine. I saw some people who had this as their setup. They had that ax was equal to 6x. That's great. You get that a is equal to 6 when you do that, right? Divide both sides by x. Super good. This is kind of nice because it helps you keep track of why it is you are getting the system that you're getting. So actually, I do like that setup. All right, questions with our second example. Okay, I want to look at like a special case here, not like a special case. These are decompositions that we are frankly just not going to do. But I want you to know how you theoretically could do them. The thing to note with our decompositions, each of the terms is always going to be essentially a polynomial that is 1 degree less under this, or over a polynomial, obviously, then that is 1 degree more. What that means is that when we have our linear factors like this, we get a constant term divided by the linear factor. But in theory, we could have an irreducible, higher powered factor as well that we would have to deal with. Let me give kind of an example here. Let me not just talk about this. If, for instance, we had, let's say, x squared plus 7x plus 12 over x minus 5 times x squared plus 4. The thing to note about x squared plus 4 is that it does not have any real zeros. What are the zeros of x squared plus 4? Square it and then add 4. Say again. Plus or minus 2i. And so we couldn't proceed to factor this any more than what we already have. And the way that we would do the decomp in this case, we would do the a over x minus 5, just like normal. But then for our x squared plus 4 term, rather than having just like a b, what we have is a linear equation. This would be bx plus c. We're not going to see anything like that. I just want you to be like aware that with the a and then the b and then the c, what we're doing that for now is just because they're the linear factors. In theory, we could have nonlinear factors as well. And that's how you would deal with it. So like, for instance, if I gave you like, oh, that would be entertaining. If I gave you something like x to the fourth plus 4, right? Something like this, which is an irreducible fourth degree, then you would have like an ax cubed plus bx squared plus cx plus d. Sure. Which would be very obnoxious to solve. Very obnoxious and also possibly impossible. Possibly impossible. That's probably not impossible. I take it back. It's not possible, but difficult. Okay. So we're not going to see examples like that in the context of this class, but they're not like all that much crazier. You'd get like a 3x3 matrix or a 3x3 system of equations, solve it that way. Nothing too crazy. Yes. Can you go water? Yeah, absolutely. Grab the pass you go. Okay. Let's look at one final example. Try this one. I'm gonna help you guys get started on it, and then I want you to find it yourself. Take the pattern and extrapolate it. What would the decomposition look like for something like this? Very nice. And now here's the tricky part. What would I need to multiply, let's say, my first fraction by in order to make its denominator match to my original? This is a new one. I'm giving you, this is like a bonus problem that I'm giving you. So not only, sorry, this should be a +1. I need to multiply not just by one factor, but both by the x minus 2 factor and the x plus 1 factor, which Sanjeev is correct here, x minus 2 times x plus 1, giving us x squared minus x minus 2. We would take this and multiply it on the top and the bottom here, x squared minus x plus 2 over the x minus 2 times x plus 1. A little messy. So in order to make the denominators match, we can't just multiply by one of the linear factors. We have to multiply by all of the ones that we're missing. So in this case, we're missing the x minus 2 and we're missing the x plus 1. So we can multiply both of those. And to do that simultaneously, I just took that product here. And then that'll just make my life a little bit easier. What would we have to multiply my middle term by? X plus 2 and x plus 1. So we would need to find that product. And then what would we need to multiply my C term by? X plus 2 and an x minus 2. All right, try to find A, B, and C. Go to. Yeah, that's probably not today. No, just interpret them. Nice.
That's it.
Very good.
My birthday's coming soon, right? January 12th.
This looks good. And so then you're just going to do this one plus.
I'm just gonna wait till you finish.
Just happy that this.
It's
All Monday, yes.
Well, how come you're?
Why do we have another Monday?
Yeah, why do you?
3 Monday.
What, that's just how it falls.
Can we not do it Friday?
Or Tuesday.
We could theoretically do it Friday, but I would need to condense the Tuesday lesson into one day.
So on Friday.
Let's do it Tuesday. Yeah, Tuesday.
Nah. We're doing calculus on Tuesday, guys. Get excited.
Freak out.
We're done with this stuff.
I know, but I don't. Mr. Burger.
We'll be doing review too. Yeah, we'll be doing review.
I have a question.
Okay,
so I'm taking home health next semester, but this one would also be resting for next semester, so.
Okay, you're doing Google Calculus.
Yeah.
Maybe no idea where.
Is it hard?
It's just different. It's not necessarily like the box, it's just different.
Yeah,
You're theoretically you do ABC. But the calculators are actually. Yeah.
I don't think I want to.
I just think I would like to which
then I don't know if I should put this one on. Yeah, here.
Yeah, I need to. That's called document. Oh, is it?
Seen a 19. It's a
It's.
I would double check.
Yeah.
Just like the math.
It looks like there's like,
Yeah. Doctor's office.
You know, math receipts.
Of the right. Like
brushing.
direct the right.
Gotta go to the air.
Yeah, and then you're getting like the sugar beet, and then you write sometimes. 3x3.
Wow. Magic.
They're faster than tomorrow.
Ben, rating was.
Jeez, too.
I'll see you.
You got it, guys.
Figure it out. Like it just doesn't. It just is.
For me.
For Ben. I'm just kidding.
Yeah. It's all my mom's. Yep.
It's like that.
No, my dad.
Funny thing. I don't know.
That's funny.
So you're adding all of them together. So collect your x squared terms, your x terms, and then your linear terms. And then you'll get you'll use that to get a 3x3.
I'm in fact not
Well,
having.
that's, you're referring back up to the 3x multiplication. So what should your x squared be equal to? What should your x's be equal to?
Just put
Yeah, very nice. Yeah. 0x squared. How many x squared?
3. Zero.
You're at 0, right? Set those in your.
It's all 0. It's all 0.
So this is what you're multiplying A by.
No, it's.
What answer?
Yeah, so and then I would collect your x squares, your x's, and then your x's. And that's what we'll use to get your x. Yeah, so like x plus b plus c times x squared.
Is this an advanced problem?
Yeah, this is. Yeah.
Dang, what the heck? Brady.
Oh, wait, maybe we don't.
Come on.
This part.
No one.
That's
everything.
And then you can group your X squared. We'll get.
Stay on my madness, like I'm using. Have a brother all yours.
Not your bro.
In my
Yeah. Wake up. Let's go. Let's
All right, let's showcase this. So we already found the product that we were going to get with A. What is the thing that we're going to multiply B by? If I multiply it all out. What'd you guys get? X squared plus 3x plus 2. Very nice, Jackson. And then what are we going to multiply C by? X squared minus 4. And so multiplying all of these out, I get that this should be equal to ax squared minus ax minus 2a. I'm going to give myself a little bit more room here, actually. Plus bx squared plus 3bx plus 2b plus cx squared minus 4c, all divided by this x plus 2 times x minus 2 times x plus 1. And I'm going to do the same thing that I did before, exact same thing that I did before. I'm going to group my like terms. All right. In this case, we have x squareds, we have x's, and we have constant terms. This should be a plus b plus c times x squared plus negative a plus 3b, no c term in this case, times x, plus negative 2a plus 2b minus 4c for our constant term, all divided by this x plus 2 times x minus 2 times x plus 1. Oh no, if you just jump straight to the system, that's fine. I'm just, for posterity, I'm just showcasing all this. Well, because it's going to be living on the internet. Yes. You totally could. And that could maybe make the solving process a little bit easier if you let off by dividing by 2. Sure. Yeah. Nothing wrong with that. Yeah, we're gonna finish it. Okay, so let's consider here what our system of equations is going to look like. What is this going to be equal to? That's equal to 0. Notice that we don't have an x squared term in our numerator. And so we know that wow, that's terrible. A plus B plus C should be equal to 0. What is this going to be equal to? That should be equal to the 3 here. A plus 3B should be equal to 3. And what is our final one going to be equal to here? that should be equal to 18. So in this case, negative 2a plus 2b minus 4c is equal to 18. In this case, we've got a 3 by 3 to solve. We were doing that yesterday. What's our general strategy for solving a 3 by 3? Do substitution, get it down to a 2 by 2. You could also do elimination, get it down to a 2 by 2. Either way is fine. For instance, if I solve my middle equation for a, that one's kind of a nice, easy one. I get that a is equal to 3b minus 3. Subtract, divide by -1. And from there, I can take this and replace it where else I see a. So in this case, 3b minus 3 plus b plus c is equal to 0. And -2 times 3b minus 3 plus 2b minus 4c is equal to 18. Or, condensing things, this is 4b plus c is equal to 3. And -4b minus 4c is equal to 12. What would you guys do from here? Just add them. Yeah, this is already set up really nicely for elimination. A little bit lucky in that case. So just adding them together. What do we get for C? -5. If C is -5, what are we going to get for B here? Yep, B would be 2. And if B is 2, what do we get for A? 3. Very nice. And so our decomposition, double check which one was A, which one was B, +2 minus 2 plus 1. Decomposition is going to be 3 over x plus 2 over x minus 2 minus 5 over x plus 1. Very cool. All right, questions here with 9.4, partial fraction decom. All right. Cool. So rest of the week, we will have a quiz.